how would you explain in an intuitive way the particle side? I read a couple of things. The more I read, the more confused I am. And I don't think that what I read, even those guys are agreed. Everybody has their own. So, I mean, there's no 100% voting here.
I saw some good visualizations of that, and I might be able to send me a note. I'll see if I can dig it up.
Okay.
And sometimes that'll help.
I'll put it on a Slack. So, yep. Because when you say particle, first of all, I'm questioning, did they choose the right word? Because you see, for the layman world, particle means something that you can, it's a particle, it's a small little thing, right? Something that you can weight it. But it's not so. I mean, I don't know, maybe so, I don't know. Some people are saying, no, it's not. Some people are saying it has zero mass, rest mass, but it has mass when during speed. Some people are saying it doesn't have mass at all. I'm totally
agreed.
So that's I'm wondering what's your understanding of particle side of light?
Terrell, is that question directed to you or the group?
To me? No, it's
to everybody.
I see the pink fingers go, no, that guy over there.
I'm not prepared. I'm not capable.
So the one thing I know for sure is that if you take a look at the history of science, and we should probably get going soon, what we absolutely knew in the 1700s about the structure of the atom was completely replaced in the 1800s. We knew it, man. We absolutely, nose to toes, we knew what that atom was shaped with. From the 1800s to the 1900s, completely replaced again. And pre-Einstein, it got replaced even further. So what we think we know about science has the same likelihood of being completely replaced in the next 100 years as it has been in the previous 100 years. The pattern holds. So, I mean, if you even look back to phlogiston, before the caloric idea, they thought that heat behaved entirely different. They had an entirely different system, and there were two competing camps in science at that time. One that believed that in the caloric philosophy, the caloric theology, so to speak, and then the other one was phlogiston. This wonderful history lesson there to see the behavior of scientists in those spaces, and it's very telling for today. There's a really good teaching company course on it called Science Wars, how scientists know what they know and why they know what they know. It's a very, really great course to pick up on to kind of get a better perspective on that.
Okay. So I'm going to put the reminder on Slack, Matt. Is that okay?
Yes, sir.
Or should I send it directly to you?
Directly to me would be good too. That way I'll act on it.
On Slack?
No, send it directly to me as an email because my Slack skills aren't that good.
Oh, I see.
Yeah, I'm just trying to climb the Slack curve myself.
Wondering if I have your
Hey, folks, before we get started here, I don't know, can you see that? I guess there's the green part of this book. This is a really awesome book. I got it about a week ago. I'll put it in the chat. It's a student's guide to waves, and it's sweet. It really gets into waves, and I actually understand it. Well, not that page, but it's a really good book. I highly recommend. It's not, it's not for quantum computing per se, but it's on waves, which is quantum computing, and the math behind it and stuff. It's pretty sweet. Anyway, Matt, you ready?
Yes, sir.
Anybody else? Everybody? I've got everybody on unmutable, self-unmutable. So we'll try with Matt's continued permission to, if you got a question, just unmute yourself and ask away. All right? Okay. Not you, Matt. I'm asking everybody and nobody's answering.
That's because they're all on mute.
I was expecting 500 people to say yes.
That's good.
There we go. Thank you, Alex.
All right.
All
All right.
right.
I'm going to go ahead
Share
and
screen.
share my screen.
And give us as much real estate on your screen as you can, Matt.
I will do that.
Play.
Now, I do notice that we've got a number of new folks on the docket today.
Oh, wow. Welcome.
And so what I'm going to do, so welcome everybody. I'm going to do a quick recap for the new folks just to catch up to speed. And I'm going to turn my video off because I'm going to look at a different screen right here and you don't need to see me looking away. But yeah, we've got quite a few. So I'm going to do a quick review of what we've covered because this is a series. And let's see if I can give you a little bit more. Oops, that's a little bit too much. I'll go up and down as we can to
there
give
you go.
Some screen.
Yeah, thanks.
So I'm going to give the good folks here just a real quick refresher. This is a series of presentations. There's actually 7 modules. It's built for a different purpose. It's built for sort of a hands-on approach where I've got where I would normally deliver this in person. We'd have a room full of people with laptops. They'd all sort of fire up to the same online space. They'd all get their own area and they'd run through these examples themselves. This is meant to be an experiential journey, learning by experience rather than sort of lecture. So you'll see a lot of examples here. We're going to do a lot of stuff live. But it is a series and it's meant to build on each other. So for the new folks out there, I want to do just sort of a quick recap of what we've covered so far and why and where we're going to go. Because today is going to be a little bit of a shorter kind of a presentation. We'll go through some interesting concepts. But on Wednesday and Friday, we're going to get into some really dense stuff. So make sure you've got that coffee brewing and you're ready to go because we're going to cover some pretty solid stuff. This basic tenet of what we're doing here is hands-on learning engagement. That's sort of the basic backdrop. And it's meant to appeal to those non-physicists, non-mathematical folks, and we'll show you why. It's meant to gear towards more of the software engineering folks. So it's not meant for PhDs. So if you're a PhD in this space, you might be bored, although maybe I'll show you a few interesting things. But if you are interested in having a solid conceptual understanding via experiential, then this is kind of what this would hit that sweet spot for you. So you'll see we cover a number of things. We'll cover quick preparation and primer. I'll fly through that. We've covered that already last week, and we did the Qubit and blocks for. We'll just kind of walk through those real fast. We've already done the quantum circuits as well, and I'll do a quick recap of what those things are just so you know what we've covered. We're going to head into quantum concepts today. So these are the basic concepts that we'll dig into and try to ferret out the nuances like superposition, entanglement, teleportation, all that kind of neat stuff. That'll build us up with all of these things to simple quantum algorithms and then quantum problems and practicals and then following up with quantum machine learning just to kind of give us a rounded out thing. This is meant to be an exposure oriented thing, not necessarily teaching the fundamentals from the ground up bit by bit. It's more or less giving people a flavor of it and then through that encounter getting some concepts across. The other thing is that it's meant to, and I'll see this in a second, it's meant to be concept specific because I'm really concerned about the ingestion and intuitive nature, the intuitive building around concepts rather than the individual frameworks that we use to articulate those and to dig around those. And you'll see that because we'll look at a single concept through a number of different frameworks. And there's a good reason why. So let's have a look at why that is. This particular preparation primer really goes through how we do what we do. We cover a little bit of context. We're going to do that now. And then we cover a lot of the tools we use like circuit first and demonstration videos and interactive, Fed interactive. We'll look at circle notation and many of these other things that you'll see, Quark and quantum playground, quantum gate playground and QEC engine and QIS kit, all of these neat things. But let's just get here to give you some background as to why I put this stuff together. what audience I'm looking for and the value that I think it has. So I'm looking at the camps of quantum, and there's a producer camp, the folks who make the tech. Now, we're not concerned about those. You need a PhD to be in that space. You need to be a math major or a quantum physicist. There's the guys making the tech. There's a war going on there. Somebody's going to emerge as a standards, and there's just standards wherever we go. But somebody's going to win that war, and they're going to hand us some tech. And although this is these are fantastically wonderful people, but it's a small group. The consumers, on the other hand, are the folks going to take that and actually go through the enterprise in the business sense or technical sense, or, in our case, healthcare sense, and use that to solve problems that are of concern in the greater organization. Now, the consultants are hybrid. We're not going to talk about those. But these guys, the consumers, the people going to take this tech and actually do something with it, have very different educational needs. And that's why I made this. So the first need they have is software engineering. They don't need to know math, opaque math, and dense quantum physics, but they do need to know how to engineer this stuff software-wise. And because they're interacting with business people and stakeholders of many different sorts, they need professional consultancy skills. Now, we're not covering that, but do need those. We're going to cover this part here. These consultants could be hybrid. They can go back and forth. That'll be an interesting group. And if you're going to spell out a roadmap for a large organization to do this kind of stuff, until quantum computing is ubiquitous, you can go to Walmart, pick one off the shelf, throw it on your shoulder, go home and use it. The only business productivity that you have, the things that can say, why am I justified in doing what I'm doing, is basically defensive publishing and patents. So we're looking at developing a patent portfolio. If you re-engineer this backwards all the way to somebody who's got no quantum computing knowledge at all, you have some very discrete steps you got to take to get along that road. One of them is just getting introduced to stuff in a way that you can digest it. That's what this is all about. The second thing is you got to sort of get a practical background, and we're building this because I'm building a course inside of Optum to do this. And then once you get engineers here, the secret sauce is how do you apply that in the greater organization. That's the next step right there. So that's really kind of what we have. There's a bunch of key issues here that I think everybody's fairly aware of, but that was kind of a perspective that we're starting from. Then we jumped into qubits and we did a pretty deep dive here. We went into sort of the foundations of all of that, classical bits and quantum bits and block spheres and radians and points in the block sphere and amplitudes and magnitudes, phases and all of that kind of stuff. And then we took a deeper dive into phase and magnitudes and how they relate to the block sphere. This is very important because we're going to use that. We're going to touch on that a little bit this week, but next week, or next presentation on Wednesday, we're jumping into phase logic, magnitude logic, very heads-on to see how they play a real key part in quantum algorithm development. So we get into phases and magnitude here. We did that already in block sphere. And then we looked at single qubit gate rotations. How do you actually, you got a qubit, you're going to establish some pulse sequence to move it around to do some kind of information processing. What are your tools? And can you build other tools from those tools? We looked at what's stock given us generally and then said, you know what, we can actually build new tools with these other tools because there's a certain logic there. And so we looked into the root of NOT gate and really showed that in all of its glory. So that was the qubit and block sphere. Last Friday, we jumped into quantum gates and quantum circuits. Now, most folks may not have a computer architecture background. And in much of what we do in quantum computing, it has a lot of similarities as well as doppelgangers in the assembler programming space, the digital logic space. And there's even quantum logic of their doppelgangers. And so we started looking at that. We looked at NOT gates and NAND gates and all that kind of stuff. Moved all the way up to full adders and simple computer architectures to show just the digital logic and how digital logic can solve problems. Then we got into multi-qubit gates, so NOT, C-NOT, not really NOT, but C-NOTs and CC-NOT gates, and we explored those. How do they work? How do they function? Swap gate and C-swap gate, because those multi-qubit gates are very important. Then we mapped them to digital logic, Boolean logic, digital logic to quantum logic operations. There are very distinct, good mappings going on there. And then we use those to build a simple adder and decrementer, incrementer and decrementer like most folks do in that space. And that took us through quantum gates and quantum circuits. Now, what we're going to talk about today is make a slight deviation from that and just get into some of the standard stock concepts. And this is stuff that everyone's heard about. But we'll look into some of the nuances and look at some of the use cases in detail. That's going to be what we do today. Now, I'm going to give you a primer on what we're going to do when we get into simple quantum algorithms. We're going to look at perfect coin algorithm, Deutsch algorithm, Deutsch algorithm. We'll get into, this is where some very interesting things, we'll get into C-phase representations, phase kickback, phase logic, amplitude logic, and quantum Fourier transforms as they pertain to building quantum algorithms. By the time we get to Friday, we'll look at quantum problems and practicals. We start looking at logic puzzles, and we take a look at the Spy Hunter and Grover's search algorithm and see how some of these quantum algorithms we have really solve problems. And what are those, like, practical problems? What are those that we can solve? And we'll also take a small detour on Friday on quantum machine learning. I'm not going to attempt to really teach anything. That's just a flavor that we'll go through, and there's a number of things that we'll cover in that space. Support vector machines, natural gradient, and embeddings and metric learning. So that's a preview, of what we're going to see on Friday. And if I can ever get my thing to pop up here, you can't see it on my screen, but it's awful annoying. So here we are today, quantum computing concepts. So we've covered all this past. You have an idea of what we're going to cover in the future. And let's just jump into it. So many of the folks who are here the first time when we covered the Qubit, took a deep dive into Qubit, have experienced waves, interference, and superposition. We're going to retread a bit of that road. So it'll be a nice refresher for those folks. And then for those folks who are new, this will be new material. We'll get into entanglement and teleportation. But what we're going to do is dig into it from using a number of different vehicles to look at it from a number of different avenues and start ferreting out some of the nuances in this space. And if we finish early, we can always bop back and forth to some of this old material for some of the new folks on the phone and have a look at some of those. So let's just start with quantum waves. So we had the question, light's both a wave and a particle. How does that happen? And what's it's a fairly confusing space. We're not going to answer that question, but waves are important to quantum computing, so we really ought to know a little something about them. The term wave is only used as an analogy, by the way, because classical waves and quantum waves are not the same thing at all. We need to know that, but the analogy, the metaphor works for us really well. The difference, I think the key difference between classical waves and quantum waves, and you're going to see this when we get into simple quantum algorithms and then practicals and problems, is that classical waves don't have interference and quantum waves do. So we're going to cover that. And that's a big deal. There's a number of these things that are a really big deal. So interference allows us to do mathematics on waves. And you'll see these are classical waves at the very, very top here, and these are variants of quantum waves. We've got waves that can interfere, and they can either negate or they can enhance. So if it's constructive interference, and you'll see this when we get into phase kickbacks, that the constructive interference allows us to do things with quantum circuitry you just can't do with classical circuitry. So wave interference is a big thing. Waves themselves are a big thing. And for those of you who haven't had a chance to look at waves, let's look at them. And so here's a nice little vehicle for understanding waves. We'll turn on this little spigot. We'll turn this thing on its side view. And now we're looking at waves being built here. And we can play with things like amplitude. The waves get bigger. And we can do things, play with frequency. The waves get further apart, or the waves can get pretty close. And if we really wanted to, we could begin measuring these things. I always like this. It's always a fun toy. And we can see how the waves are behaving here. And particularly if we move this over here, we get a very different behavioral pattern. So it's all kinds of stuff we can do to tinker around with waves. But that is a part of quantum computing. Having some kind of understanding of that's helpful. But interference is even more important. So you get a couple of Fisher guys tossing their lures in. There's concentric circles of wave ripples. When they begin to overlap, they interfere, and we can do math with those. Again, there's that interference as well. If you want to take a look at interference, we can look at it here. And we'll turn a couple of these things on. Whoops, I turned it off actually. And you can begin to see how those waves are interfering with each other. That's a fundamental tenet. If we can exploit that in unique ways, we can do information processing that just can't be done in the classical world. And without going through all the different gyrations here, I'm just going to pass on that. Superposition is another one. So we've covered waves. That was really a drive-by. So we have sort of detailed discussions. Then we have what we call drive-by. Drive-by is we drive by, shoot a bunch of stuff, and leave. That was a drive-by. We just passed through a concept and then just motored right on. Superposition is another thing. It allows us to instead of having a single bit with 1 and 0 on and off, we can have everything in between. And that does some very interesting things for us. One of the things that it does is that any point on this sphere will have elements of both the 0 and 1 ket to it. And we've covered kets before. I assume that everybody on here understands the ket and the basic structure of the qubit. But moving into the detail a little bit, you start seeing this very familiar mathematical equation that tells us, gives us information of where that point is on the sphere that we're talking about, and that is what we call superposition. A perfect Hadamard gate gives us 50% on, 50% off, and we're going to look at that next experientially. And by the way, before I go any further, I'm just going to add a bunch of things in on the side. These materials are meant to be given away, and they're meant to be digestible on your own time. I haven't yet enriched them all the way I want to, but it will have a GitHub, so you can download this stuff and just tinker with it. So if you see things like links and stuff like that that pop up to help round out the conversation, I'll be adding many more of those as well. So just wanted to throw that bug in there. Now, on the superposition side, I think one of the things that's key is that every time we add a qubit, we effectively double the space, the state space we're working with, and then when we factor in interference, we can again, that's the things that separate quantum and quantum's capabilities from regular classical capabilities. So that we get parallelism on one side, the quantum interference allows us to effectively bias the gate when it's measured to be either a 1 or a 0 in very unique ways. So let's look at, I think in this, what we call a perfectly random qubit. Now, random number generators are interesting, but they're theoretically predictable. If you knew what the length of the string was it's using, you could predict the next number. Now, the superposition applied Hadamard, a pure superposition of a qubit is truly random. It's absolutely random, and so that makes a really great random number generator. And so what we'll look at here is, for the new folks, this is one of the new things you might see. It's a QC engine. O'Reilly's got a wonderful book. Carnegie Mellon's actually using that this year to teach their quantum courses, and we can use this. Yeah, Carnegie Mellon. And so we can run a program here. It's a fairly simple, intuitive thing, but then we can inspect the output here and watch how circle plots work. Circle plots are interesting because there's two phases represent, two parts of this represented at once. The magnitude and the phase. Magnitude is the how much of these circles actually have color in those, and then the phases will be this line here. It can go 360 degrees, or it can go X number of radians, pi base radians. So I always try to bring the folks who are new up to speed on some things you've missed as we go on, so as not to leave you behind. But the cool thing about this is we can tinker with this. We can actually inspect this, which we can't do with other frameworks. So we get a simple qubit. We initialize it to 0, we put a Hadamard gate on it. Now you will see that the phases haven't changed, but the magnitudes certainly had. And and we can measure that. And that's a 1. We can apply another Hadamard gate to it, measure it, and there's a 0. So under the hood, this is purely random. The simulator that we're using is the ideal state of this quantum expression, and it's completely random for our purposes. So that's just using this to show sort of a randomized single qubit put in superposition. There's superposition, and then we render it, measure it again, and there's a 1, there's a 0. So it's neat that way. Quark is another vehicle that we can use to draw intuition. This idea of developing intuition around a subject is extraordinarily important. And the reason it's important, and I'm going to bring you back here, is because we don't know who's going to win this war. We don't know what framework is going to be the dominant framework moving forward. These guys don't even know. So in order for us to prepare preemptively to be able to use what these guys give us, we have to use every framework we can and focus on the conceptual understanding more so than the implementation framework. That cannot be undersold, and so we're going to look at the same thing through another mechanism that gives us a little bit more intuition with that. So here we have basically how to mark gate, and we've got this. Quark is a wonderful explanatory teaching tool. We can move gates in and out as we want and create things. So here we've got Hadamard gates, qubit that's put in superposition, and we're running this message thing through it that basically randomly goes through here. And as you can see, these are different ways of looking at the internals of that qubit. We can look at the chance of being on measured, and as you can see, it's going up and down. You can take a look at the blocks for representation, and that's got all of the phi and psi and the various rotation axes. You've got the z and the y and the x are all rotating around. And then you can come over here and inspect the individual amplitudes of the 0 and 1 ket here, and you can see everything's really moving. The faces are moving, the magnitude square is moving, and all of that. And so that's just another way of looking at a tool that gives us insights as to the behavior patterns of this thing in a number of different ways where this particular tool may not have been able to do that. Gives us insights into the behavior patterns of this, and that's what we need. And then of course we can just jump right into QIS kit. I mean, we could have, we've got to make sure that IBM gets their due because they're the 500-pound gorilla in the room. And right now we've run this, we'll just run this. So this is a state, gives us the counts, an output state of the amplitudes, and the amplitude is 100% 1 and 0% 0. And then we can do a quick display state of what that is. But let's run that and run it a couple times and run it another couple times. This is really stubborn. There it is. So we get a change. We can also print out the polar coordinates of that. We do that elsewhere. It's not really intuitive now, but other areas when we deal with phase changes, that's very intuitive. So I always kind of throw that in there. Now we could do that with a bit. What about a byte? So this is a perfectly random byte, a Q byte. And so, the great thing about using QSKit is that we could run that again, and we can see the behavioral pattern manifest. Now down here is sort of the circled plots, and as you can see, there's a lot of circles in that plot. And as we begin to look to this and watch that function move forward, we actually get a number. In this case, it's 176. Now that won't change unless I actually rerun the program. And then it will give me another number down here, 103 and 183, or 104 and 183. And really what we're doing is we're initializing a bunch of qubits. As you can see, all these spaces from, this is binary addition. For those of you folks who weren't here, one of the things we did cover is much of this stuff is binary. So we have to look at these certain places, and we just run them all the way through, and you get a certain randomized number, but it's a Q byte. We can also do that with Quark. So the beauty of this is, we take 8 bits, and we've got 256 states we can use. Now that's interesting to look at in paper, but when you actually see it in action, whoops, where are we here? And you can see every byte, every extra qubit that we add adds a significant amount of practically, it effectively doubles the state space. We've got a lot of parallel work going on here. And that's the beauty of, it's another one of those differentials in quantum computing we just don't see in the classical world. And of course, we can use QSKit to look at that as well. Let's just have a look at that. We've got the binary representation and the digital representation of that too, as we run that same thing. So we come out with 188, we'll run it again, and we come out with 84, and we've got the printout of the circuit. Now, if all you had to work with was QSKit, if all you had to work with was Quark, if all you had to work with was QC Engine, you'd miss some of this stuff. There's a lot of other tools we use throughout this, but you'll see these are some of the big ones. You'd miss those opportunities to observe the behavior of some of these concepts under the hood. And that's why I will always stress you need to have many different angles to look at these things. The concepts are far more important than the implementation framework right now. We'll worry about the implementation, whoever wins the standards war will work that out. So that was, interesting enough, that was, where are we here? That was superposition. Now we're going to get into entanglement and teleportation. Things get a little bit more interesting down here. Again, this is stuff that everybody knows, the first couple of chapters that you pick up of a quantum computing book, but there's nuances to all of this. And if we get through this material fast and we want to go back through some of the old material for some of the new folks on the line, I'd be very happy to do that. There's a lot of interesting stuff we've covered already. So entanglement, I like entanglement because it's the subatomic particle version of being married, right? So if you're a single person, you have your own state, you have your own personality, you have your own money, you've got your own time, it's all there. And then you get married and that changes. That you have now a shared state. It's not your own anymore, and you've shared a state with another entity out there, and what affects one absolutely affects another. And so that's kind of the neat thing about it. Entanglement, from a conceptual point of view, from a practical point of view, you need entanglement to do some really interesting things. When we get into phase logic, not quantum digital logic, but quantum phase logic, you'll see that entanglement looms large. It's used everywhere. It does some very interesting things, particularly managing phase kickback and managing interference. So, and it helps us scale, and scaling is very important too. So there's a couple of really good background videos here. And I think what we'll do is we'll explore some of the nuances with some of these tools. So one of the things we can do is an entanglement gate is really easy. It's a Hadamard gate and a C-knot. That's it. Boom. They're both entangled. Now, under the hood, that entanglement process is being implemented with mathematics. So the math tells us it works. But one of the things you'll notice, even up here, I'm just going to come back up here for a second. And all of these things, particularly here, particularly up here, like you don't see the relationships under the hood with this this symbolic tool that's giving you information. And if all you looked at was the relationship of the information on screen, you'd be missing something. And one of the things that I found is that, if you think that a circuit gate is going to tell you everything you need to know, you're absolutely wrong, because it won't. You have to look at the code, and you have to understand what's happening under the hood. That's a hefty lesson to learn. So what we'll do here, but some vehicles work better than others. This one does a really great job because we've established a Hadamard gate with a C-knot, and that's the entangled circuit, and we can put a message queue up here to institute changes that we can observe the behavior and many of these other mechanisms that allow us to look into that. But there's a few things that need to be put in order. The first one is, let me go back up to here. Do you see these gates? These are the block sphere representations. And you can see the points in those block spheres are moving around, right? Because these are not entangled. They're separate. They're individual things. And all of these points are moving around independently or on their own. When we entangle that, the block sphere representation quits. It stops. It's given up. And that's because these states of these particular qubits can no longer be described independently. And that's one of the key things of entanglement. Now we can do whatever we do to one happens to another. So I think that's important, and you can visually see that in Quark, because when you have when you take that out of the picture, the Hadamard gate out of the picture, now both of these things can be described independently. But when you put that puppy back in, now all of a sudden the block sphere, this representation quits. It can't describe it anymore, so it stops. But then we can look at its behavioral pattern here, because the messages gate is pushing a lot of information through, and we can see how it behaves over here. But I think that's a big important point, at least through this tool. We can look at that and we go, why is that there? I bet there's some entanglement going on there. Another thing we can do is look at multiple entangle gates. Oh, by the way, let me just go back up here. I can take this message gate and go back up and down all I want, and absolutely nothing is going to change here, because what happens to one qubit happens to the other. With the things that affect one qubit automatically affect the other. So we don't see any major changes here. And that's kind of interesting. It gets more apparent when we entangle multiple qubits, which is effectively what we're doing here. And as we move the messaging up and down each one of these, what happens over here and over here, well, particularly in this side, doesn't really change much at all. And I think that's important. It's just another way of viewing this entanglement process that gives us a little bit more intuition here. And there's a lot more information in games and experiments that we can run with a tool like this to gain better insights. And when we start developing quantum algorithms, we're going to need all the insights and intuitive understanding we can get. So we can also use the QC engine to explore a couple of entangled qubits as well. And I've got that running down here. This is a standard entanglement gate, and really all that does for our purposes is produce either a 1-1 or a 1-0 or a 0-0. One of the things you can see here, though, is that the behavior of these qubits under the hood is relatively interesting, as depicted from this particular framework. And there's a whole lot of reading about how those can behave in the book. I will reference you to that because that's an excellent book. It is a little bit dense, but it's worthwhile. And of course, we can get into QIS-Kit and say, okay, let's have a look at a couple of entangled qubits. We've got a bunch of code here. I'm not going to bore you with that or burden you with that, but effectively we can run that too, and then we get either 1-1 or a 0-0 each time we run this. There's the 1-1. We can print out the states as well. There's not too much intuitively here, but these circle plots are very helpful as well. So as you can see, it's number 3, and in terms of binary states, that is 3. That's entanglement. That's sort of a nuanced approach to a simple concept of entanglement. What we're going to do here is get into teleportation. So Terrell, now we had talked about the process of doing a bio break.
Yeah.
And right now, given the way that this material lays out, would be a perfect time to do that. So if you want to do a 5-minute bio break for the team, we can come back here and I can head into quantum teleportation. I think we're going to end early, and maybe we can go with the new folks on the phone who want to explore some of the old stuff that we have. We could cater to that crowd too.
Okay, so you want me to take a bio break while you answer questions? Is that what you just said?
No, I think it's going to be a bio break for the entire group.
Everybody.
Everybody gets to use the loo, yeah.
So I'm not special?
You're always special, but we'll give the team a chance to do a break, get some coffee, use the loo, and then I'll let you set the timer and we can reconvene.
How much you want? 5 minutes?
5 minutes, 8 minutes would be fine.
8 minutes?
Yep.
A little OT, okay. All right, I'll set it for 8 minutes. So I can
all right, everybody, we'll be hopping back on in 8 minutes.
Let's have a word from our sponsor. I could play some of that Led Zeppelin if anybody's noticed. I'm trying to find a counter here. It's no longer available.
I'm just going to look at my wristwatch. All right. Going on mute. See you in a bit.
Ciao. Calendar. Google. Countdown. There we go.
Carol, I think Quantum Palooza is being copied by Quantum Week in June 15th through 19th. They're trying to do as many events as you've been doing.
Who's this?
Quantum
Quantum.
Week, June
The
15th
Quantum.
through 19th. They've got like they're trying to have as many speakers as you have typically.
Quantum. Well, good. Quantum Weekly. I didn't even see that. Okay, so
There's a lot of events going on right now with quantum. There's the IQT in New York taking place.
yeah,
And in 2 weeks, there's going to be the quantum tech. So it looks like a lot of activity.
well, that's why I try to put it in one place so we can keep track of it. I don't see, is it, whoever was talking to me, was it Quantum Weekly? Yeah, IQT is not free, right?
Yeah, this is,
Yeah.
QT is free though. If you go to Quantum Tech, their digital week from 15 to 19 June, that's a free event.
okay, you're talking about quantum tech. Yes, that's from
Yeah.
June 15th to 19th. I didn't know that that was free.
I mean, there is a paid version, but I doubt anyone's going to pay it for it.
I think I've got that one in the list.
It is in the list. You just don't have it for the entire week.
Oh, I just put it at the top.
Yeah, something like that.
Which one was that, Tom?
Quantum Tech, QT. You have it listed on June 18, maybe somewhere else too.
Yeah, no, I got it each day of the week. Yeah, they've got the Friday night. Is that them? It's all blurring together now. Thursday, yeah, it's the 15th. They have a startup competition. There it is, the 12th.
Well, the startup's on the 12th.
The startup's on 12th, which is a Friday before, and then the following Monday, then they go into all their events, their regular events. It starts at 7:25 a.m. New York time.
Where is the link for the startup stuff? Oh, I see it. It's a separate link. I
So
got it.
it'd be Friday. But who was the one who made the point about Quantum Week? Whoever that was. I'm missing the point there, because when I go to Quantum Weekly,
I wasn't talking about Quantum Week. I was talking about this. I was talking
Yeah.
about this week.
That's you, Tom, but somebody before you, I didn't recognize the voice.
That was me.
Who's that? That was you, Tom?
Yeah, it was me.
Oh, okay. Sorry. So is that Quantum Week or Quantum Weekly?
I was talking about quantum tech.
Okay.
It was just that it was a week long. That's all.
Oh, I'm sorry. Yeah, I'm a space cadet. So, yeah, so I got that in there. Just trying to keep track of the, the free stuff.
Yeah, the investor showcase on that Friday looks pretty interesting, actually. It's not going to be that long. It's going to be, kind of like noon British time to like 4 p.m.
Yeah.
And probably only 2 hours of it's going to be public. Or maybe all 4 hours will be public. Hard to say.
Yeah, I've got it 6:45 our time, so I got 5 hours total, 7 to 12. Of course, I'm doing it with 12 things going on at one time, so a lot of error there. By the way, Tom, you can see I got the time zone converter thing minimized.
I saw that.
So I think I'll settle in on that. If somebody pushes that button, I can't do much. But where are we? Okay, Matt should be coming back in a little less than 2 minutes, people.
Yep, I'm ready to go. So just give me the green light and we'll continue on.
Okay, everybody who's back, if you give the thumb up, the Zoom reaction with a thumb up, that means you're ready. We'll start early. If not, we'll just wait out the minute and a half. Hey, Iman, you want to tell us about your training one of these days, by the way? Is everybody aware Iman's got like a bunch of training down on his site? I forget what it is off the top of my head. Iman, you in?
Yep, he's on
On text.
He's taking advantage of that 8-minute break.
Yeah, I think he's back. He's texting everyone. Hopefully.
Oh, is he?
Yeah, he's on mute right now. So. Doesn't seem to be able to. He doesn't seem to be able to get off of mute.
He's clapping. He's giving hand signals. All right. Well, one of these days, Wednesday or Friday, mention it. He's got a bunch of content down there, by the way. Bunch of videos and other stuff. Homework, like assignments or quizzes or whatever. Yep, got a thumbs up from Keeper.
Is Keeper on here?
Keeper's on here.
You can go profile.
Oh.
Can you hear that?
Yeah.
Yes, we can.
See, when I shared the screen, I did not share the computer sound. You should not be sharing that. You should not be hearing that.
We definitely do hear that.
Oh, do you want to hear it more?
Nope, I think we're good.
All right. Well, take it over, dude.
All right. Thank you very much. Welcome back, everyone. And
screen share.
Oh, am I not screen sharing? Let's do the screen share. Thank you very much.
Alrighty then.
There we go. Just gonna grab some water. So welcome back, everyone. It's a pleasure to see that we've gone up to 37 now. So great stuff. I think that we'll probably get through this bit of material fairly quickly, and then I think what we could probably do is go through some of the older stuff for the folks on the phone who have missed those other couple of presentations on a request basis. So, so this is quantum teleportation. Now, we've covered to date in this particular foray waves, interference, superposition. We've sort of done a drive-by there. Gone a little bit more into superposition, a little bit more entanglement. Let's get into teleportation. So more of a detailed discussion there. And then we can go from there. I like teleportation. It's a neat experience. I was a Trekkie, and so I usually have that as sort of a mind virus to think of how quantum teleportation really works, but it's not really how it works. It's a fundamental primitive in quantum networking and cryptography. That's pretty well common knowledge. Got a bunch of neat background videos here for you. But I want to get into the nuances of that, that phenomena a little bit. And really, we're not beam me up, Scotty, no intelligent life down here kind of thing. We're really, what we're doing is we're transporting states. A state of a qubit is probably the easiest way to begin to wrap our heads around the mechanics of all of this. So the particular qubit has a state, and it's being transported to another qubit. That's really the fundamental process. How do we get some state here and transfer it over there? And so we use entanglement as a connective substrate to do that. So we're going to dig into this a whole lot more down here, but let's just kind of look at this picture here. So if we have an entangled pair, B and C, that are being shared between entity A and entity C, then we bring in, when we fuse, and this is sort of the larger picture, we're going to dig into the nuances of this in a minute, so I'm really going to do a drive-by, but we fuse a state, particular state, with a shared state that's entangled, and effectively the qubits that are being held over here sort of immediately change into an indeterminate state because something happened over here. A state's been fused together with this, and you can't really tell what message or what state has been transferred until these classical bits via a conventional mechanism gets transferred over as well. And that you'll find ends up being like a spin up, spin down thing. Once those are reconstituted with the state that's been transferred over, and you'll see this in detail as we dig into this, then the state can be reconstructed. And that's effectively how that works. And this is really kind of a fundamental principle, since we can't copy qubits, of quantum networking. So let's look at this in a little bit more detail. And then we're going to go into the QE engine and really look at it in further detail. So this will be kind of like a case study for us. So I've got things marked off. This is a very busy screen. And I've got things marked off in semi-order. So you've got 1, 2A, and 2B. You've got 3 around here somewhere, 4, 5, 6, 7, and 8. So we've got a process that we can begin to follow with nice bright colors to try to articulate what's happening under the hood, in lieu of a further discussion when we start playing around with some of the materials here to try to further tease out those nuances and try to hone in on those concepts. So let's start with an entangled pair. We talked about entanglement. I think it's you get entanglement the very first time you open up page number 1 of a quantum computing book. But we've got 2 qubits that we entangle through some process. And that's our conduit. That's our communication conduit. And so one gets distributed to Alice, who's always a protagonist, and the other one gets distributed to Bob. So these entangled photons, qubits, are now distributed to these 2 entities. And that gives us our communication, a quantum connection. This is how we're going to sort of transfer the states. Now, Alice has another qubit, P1, and that's got a certain state to it. We don't know what that state is. We don't care what that state is just yet. But we want to get this state over to Bob. And we want to do it quantumly. So this is kind of how that works. So when this particular qubit gets combined with this one, then that fusion, you're going to see that we'll end up doing a Hadamard gate to make sure that both the phase and the magnitude information are maintained and dispatched appropriately. And then we'll do a measurement. The measurement does the dispatchment. The Hadamard gate, as you'll see when we go through the use case, maintains it, or else it would be destroyed. But nonetheless, when these 2 photons, these 2 qubits are combined, and then they're measured, they both get destroyed. It's a property of how this thing works. Now, once that happens, the original state of P1 gets shot over here. However, so there's 5A and 5B. It's an indeterminate state. So whatever Bob has all of a sudden goes into a state where he goes, okay, I know something happened. I just don't know what it is. Now, what effectively happened was that the state of this particular qubit got transferred over here, but they don't know what it was until the spins, effectively, the directions of the spin from here to classical bits that can't go over quantum, has to go over a conventional classical connection, gets sent over here, whether you pick up the phone and say up, up, or down, down, or up, down, or down, up. The spins get articulated. Once he knows what those spins are, then he can reconstitute this this qubit, and he gets back the original state. And so, excuse me, we've effectively transferred the state over. Now, to do that, 2 classical bits have to get transferred, and that's a must. But other than that, it's a pretty interesting phenomena that we're able to do. So this is sort of the roadmap that we're going to look through, and I want you to sort of keep this in mind, and I may come back to this as we embark on this next bit of the conversation. But what we're going to do is take a developmental detour of walking through the circuit and the program. And what we'll do is we've actually gone over here, and we have that up here, and we can step through it. Now, it doesn't do you much good. There's so much under the hood that's actually involved in the code here of understanding what's really happening, that we want to walk through the narrative first. We want to investigate the use case first to get a feel for what all is happening in this really classical use case. There's so much under the hood. It really, it's of value to do that. So we'll step through all these, but as what I call a drive-by again, what we'll look at is the entanglement process. Well, even before that, you've got really 3 qubits. You've got Alice, you've got the entangled pair that these two share, and you've got Bob, our standard protagonist that exists up in this conversation up here. Then you get a preparation of a payload in some certain way with some certain latent characteristics that we can identify and show later on very distinctly. We've got a re-entanglement along that shared entangled bits. And then we do a Hadamard gate and send them, measure these things. That actually sends it up, and then we receive it, and then we make a note of what we received to make sure it's the right thing, and if we really wanted to, we could verify it, which means effectively doing the absolute reverse of this and making sure that we get, in this case, a 0. If we get a 0, we've actually done that. Now, this is sort of the drive-by, but there's so many nuances that are under the hood. We really want to look at this. So let's do that. So first we're going to, now what we're effectively going to do is dissect this whole thing. And we're going to look at it bit by bit, no pun intended, not qubit by qubit, but we'll look at how the circle plots pay out, because the drama associated with this part of it and the magnitudes and the phase rotations actually give us indications of behavior of this thing under the hood, and it's worth considering. So we start off by creating an entangled pair. It's a standard thing, a Hadamard gate and a C0, and that gives us an entanglement. Now that entanglement, and by the way, I'm listing some of the code down here. So take the entangled gates, do a Hadamard for that, and we do a C0 with that gate. And so that gives us an entanglement between the entangled photons and Bob. So entangled pair and Bob. And so remember, now we've got 3 qubits, so 2 to the 3rd gives us 8 circles here. So that's our state space. And that's effectively that. You know, we don't really need to talk too much about that, but I do want you to keep in mind that, you know, we've got Hadamard gate here. Everything in terms of phases is going straight up, this neutral at this point in time, and then we go into preparing the payload. Now this is where things kind of get interesting. So you got to prepare a payload. Now these 2 qubits are entangled. Alice at this point is acting completely on her own. She's independent of these 2 right now, so she can prepare a payload. Now you've got sort of write a 0 down in the qubit that she has, and we take a Hadamard gate and do just a normal 45-degree phase shift. So it just kind of turns the dial a little bit, puts it in superposition first, turns the dial a little bit, and then puts it in takes it out of superposition. And so you can see that here. If she writes a 0, she does a Hadamard, phase 45, and then another Hadamard. So that's preparing the payload that she's going to ship out. And it's useful because it helps us see that. And what happens under the hood is you get Alice getting sort of an 85.4% on the her 0 qubit and 14.61 on that. Now, those numbers mean nothing. What we're really looking at is this right here. This is the payload for her. This is what we want to track. And so we can see those manifested elsewhere. But what we've done here is simply prepare a message. She's preparing some state to be teleported over. So once that's done, we link it. Now this is where things start getting interesting. A lot of stuff happens in just a few short operations here that I think give us clarity or raises questions, depending on what side of the fence you sit on, of how some of this stuff functions under the hood. So she's prepared a payload. She's got to send it. And I think this gives you an appreciation for what happens under the hood here. So the very first thing she does is entangles her payload to the teleportation circuit, the entangled photons. That would be akin to this right here. She's combining all of this. And where are we here? Linking the payload. Once she does that, she institutes a Hadamard gate. So she's prepared a payload and she has entangled that payload with a communications qubit that's already been entangled with someone else. And the institution of that Hadamard gate has profound effects. What that effectively does is that, and that's where we're going to move down here a little bit. When she puts the payload in the superposition, if she hadn't done that, and she executes the necessary next step, which is a read, and another read after that, she absolutely has to do both of those. When she because she instituted the Hadamard gate, it maintained both phase and magnitude information as the message got passed through the entanglement and into Bob's space. That's the thing that maintained phase and magnitude information, and that would have been destroyed had she not done that before doing that necessary read, which is the other thing that you think, wow, if you've got to do a necessary read. Yeah, absolutely. So once she did this, she maintained phase and magnitude information, and then when she hit the read, when she executed both of these reads, then it really sent that data. It pushed that data through this mutually combined communication layer, and then Bob effectively received that. So I think that in this little space of just these few operations, so much stuff happened under the hood. That's really important to note. And so that's putting this, that's sort of sending that data. And what happens is that there are 4 states that she could have sent. Bob doesn't know which ones those are. Either the first column, you'll see here, and I think what they're talking about is 4, 5, 6, and 7. In the first column, you've got Alice's payload, exactly how she prepared it. Let me just go back here to say, when Alice prepared her payload, this is the bit we were concerned about right here. When she entangled it, there was some switching going on, so some bits moved about, and that's sort of normal here. And what we have options for, and Bob doesn't know which ones these are, is that it could be any one of these 4 states. It could be the payload exactly how she prepared it. It could be slightly different with a phase rotation. It could have a number of other differences as well, but he doesn't know which one of those it is until Alice sends 2 classical bits, which are effectively phase spins, as I understand it. And then let's go back here. Once he receives it, where are we here? Oh, sorry. Yeah, Alice performs a read, so that pushes it further. And we talked about that. And so Bob actually reads those. And so this is also where you have certain bits of code. Like if you just looked at this circuit, you would not know that there are if statements back here that are supporting this. And that's the real drawback from expecting that you can look at a circuit gate and get all the information that you need to truly understand what's happening on the hood. You can't. Even in these simulators, you can't. But so you have to look at the code and the circuit gate as well as other mechanisms to truly understand what's happening. So he receives this and receives 2 classical bits and is able to reconstruct that and ends up getting this qubit right here. This is the one that we were most concerned about. This was, we go all the way up here, this was the bit that Alice prepared through this mechanism here. This was the payload that she prepared. And then through this whole process, that payload got teleported and reconstituted into Bob's space. And that effectively, going back up here again, is over here, and that's all that information, all that sort of activity that happens on this side of that teleportation fence. So hopefully that makes things a bit more clear. And if we really wanted to, we could verify it. So basically what we'd do is we take this gate and run it backwards. And if we get 0, it all checks out. If we get 1, something's gone wrong in the process. So what we could do is hop over here. Whoops. We could hop over to QE Engine to do that. Let me just come over here. And this is the gates. We can just kind of walk through this. Now, without that explanation that you've just had, that long involved case study, this may not make as much sense when we start walking through this, but here we are. We're going to take 3 qubits. We've got Alice, the entangled photons, and Bob, and we're going to entangle a pair. And that's effectively what happens when we entangle a pair. I suppose we could maybe do this to make things a little bit more like what you had seen in the discussion. So we'll entangle that pair, and then we'll prepare a payload. So this is the payload going through the gates of the phase changes and applied to second Hadamard. You can see how this is the payload that we are attempting to move into this spot, I think it is. And then we can entangle it with the this communication gate. We institute the Hadamard so that the phase and the magnitude information is maintained. We do a necessary single read and another read as well, and then that's ready. That's been sent, and then Bob receives it, and then we can see that he picks that up. And if we wanted to verify it, so that is the state that we wanted to transfer. And then if we wanted to verify that again, we could do that. And of course, we come back with that. That's effectively the 0 that we're looking at. Now, it's neat to see this. And in the book, when you read it and you go through this example, it's interesting to see that. But unless you go through in detail, where are we here? With this and really understand what's happening under the hood, it's hard to grasp that concept. And the pure purpose of this is to get that strong conceptual grasping of that that concept of how teleportation works. Now, a good way to get that is to use Quark and do something completely different. So this is a teleportation circuit in Quark, and I don't want to go into the details of what all these are. It's effectively the same process you've seen. You know, we've got the everything set up here, and we've got a message that's being constructed here, and that message is literally going over here. We've got a bunch of other mechanisms and entanglements going on here, and the state being sent over here. But down here, you can literally see that state. If you watch both these circles move, they move in unison. And what we're doing is this whole process is sending this message. What the message thing does is it sends a different message in different formats all the time. In this case, it's sort of a randomized format. So each movement across the block sphere, surface here is a single message that's being sent from this side, and you can see it's being received over here in perfect sync. And this gives us a more visual. This is one of the things that Quark is really good at. It gives us a more visual example that we can intuitively digest easily of that teleportation, and we're not using opaque mathematics or dense quantum physics to do it, but the normal man on the street can look at this and go, yep, I totally get that. So I wanted you to see that. That's an encouraging thing to see. Now I'll get into QIS-Kit and try to explore that. Now I want you to imagine what I would have to explain, or anyone else would have to explain, if this was the only tool you had. So we're basically going to set up a program. I'm not going to go through what these are, but as you can see, you've got Alice, Bob, and the quantum registers, classical registers, and we go through this whole process. Effectively, we're mimicking this circuit right here. And so we'll set that up, we'll run it, we get a count, we'll run it again, we'll get some output, we get the gate that's printed out, and then we'll just run a couple of circle plots from that. And I'll ask you a question like, did you get it? Was that intuitive? No, it wasn't. It's an awesome program to do some serious research with, but for the beginner coming up, trying to understand conceptually what's really going on, we must use multiple vehicles for understanding, because some of them just fall short of that knowledge. And unless you have that strong math and physics background to pick that up, you won't. It will be too hard. And that, ladies and gentlemen, is what I call the end. So Terrell, how about if we cater to the new folks on the line who haven't had a chance to look at any of the other presentations we did, quantum gates and circuits, the Qubit, or even, I mean, these are really the only other two deep dives we've gone into, to ask some questions about some of the stuff we did or some of the stuff we've been talking about today.
Couldn't have said it any better myself.
I'm standing at the ready, and I'm glad to be at service. I think you're going to have to unmute folks globally. Oh, start my video. Yep, starting video. Where is that? I suppose I should turn around and face the camera.
Yeah, I think the microphones are all available. Alex, looks like you pushed the button. Actually, do you guys know, if you put, at least the host, if you push the space bar and talk and release, try that. That unmutes you, by the way.
Oh, nice. Some folks are doing that.
Is that cool?
That's very cool. You could do a drive-by soundbite.
Yes, you can.
All right, so there's...
I want to make a comment for Matt. Matt, that was a really good way of intuitively looking at the teleportation in different ways. I mean, you know, I've gone through the MIT course as well, and there's a lot that you have to kind of wrap your head around before you can really understand what's happening. So I appreciate that you were showing it with different visualizations, and it takes a while to really sink in. So it's good.
Thank you. It's one of the things that I like to do is I want to try to make sure my contribution is always keenly wrapped around how much I can get you guys to understand, or whoever's in the audience to understand. It's not about me talking about me, but it's how much I can get to you. How can I inspire you? How much information can I get to you in the space that I want to do that? And that is, I want to avoid the dense math and the dense quantum physics and teach software engineers the key concepts here. So I appreciate the positive input.
And I think there's some misinformation out there about teleportation, where you can transfer a state faster than the speed of light. And I think the point that you're making over and over again, that you have to pass that classical information, you won't be able to decode your qubit till you get that classical information is very important, because even people who have been in quantum computing for a while have missed that point.
I would agree. I think there's secrets under the hood, because the entry price right now for engaging in this space is you got to know the heavy math or the quantum physics, and that keeps a lot of really good people out of this space. So we want to try to open that up for them. Now I see we have a lot of new faces on the line here. Anybody want to chime in to, if you want to look at some of the other stuff we did? We've got some old faces. Good friend Keeper Sharkey is on here. Good to see you here, madame. But some other folks, the names I haven't seen yet. So hop in and ask some questions.
Sanjay's raised his hand.
All right, Sanjay, take yourself off of mute and speak up.
Hi. So this is very interesting. I'm very glad that you are offering these types of workshops and tutorials. And this Python-based simulator is fantastic, absolutely fantastic. So I do have a question. So my readings and understanding of quantum physics, and you know the issue around entanglement. So the way that qubit superposition, entanglement, and teleportation, I mean, to me, it would seem as if they're all based on the same underlying principles in quantum physics. Is that true? Or are there actually separate, disparate reasons why these phenomena occur?
Well, entanglement's going to undergird quite a bit of that. You'll see entanglement undergird not only quantum teleportation, but when we get into next week, well, next week, I keep thinking it's next week. It's Wednesday. Well, both Wednesday and Friday, as we start getting into phase logic, entanglement looms very large. So you're going to see a whole lot of C naughts and CC naughts and all that kind of good stuff. But I think there's a handful of characteristics that and attributes and phenomena that occur at a subatomic level that we seek to exploit, that gives us those immense speed ups and unique things. And it's the combination of all that. So I think entanglement's going to be your big one. Superposition entanglement.
That's what I was saying. So is it safe? That's exactly how I was seeing it. So is it safe to say that entanglement is the underlying property upon which superposition and teleportation are based? Because, for example, to me, teleportation basically means that we are, it's not necessarily that we are teleporting matter or energy. It's basically that we are entangling a, quanta of matter at a specific location that's far, far away, or even close, but it's at a different location. And because we're entangling that specific item, we're kind of given the feeling that we're teleporting it there.
The state, yeah, definitely state, but don't fool yourself. None of this would happen unless you had superposition available to you.
Okay, all right. All right, I mean, that's something I'll have to read a little more on, because to me, superposition also would come out of entanglement.
It's a, no, not necessarily. I think superposition, you can have a qubit superposition that's not entangled. We've shown that. So let's have a look at all this. All those qubits are in superposition, right? But none of them are entangled. It's only when you decide to entangle those, like here, that at least in this simulator, the representation quits because they're a shared state. So yeah, they're not, so superposition probably happens, I would argue, many people would probably argue that happens more first before you can get any kind of an entanglement going on.
Okay, all right, thank you.
Yes, sir. Other questions? We've got, how do you say it, Hamadi?
Oh my God.
I
Everybody
butchered
says it like that. Yes, you did. Everybody calls me Hamadi.
It's a typical Western
time.
approach to trying to, to articulate an ethnic name. How bad was that?
I wonder how is it Hamadi? Like, there is no A after M, or there is no I after D. So I wonder why people come up with that pronunciation.
We're all uncultured swine over here.
It's okay. I wasn't trying to like be hard on you, but Hamadi is pretty common, like for people to call me like the first time, but it's Hamida.
Hamida. Okay, good. I will not make that mistake twice. I'm glad to have you on board.
Mida.
No worries at all. You can call me Hamadi. Not at all a problem. I don't have any question in particular, but I just wanted to say that I have an arts background, a design background, project management background. I'm not a software engineer, but this is like my first time, like learning about quantum computing. I'm very much interested in the idea of entanglement. And I just wanted to really say that I appreciate you putting it all together and making it easier for someone like me to understand, the certain, like important aspects of what it is all about. I'm starting to get a little familiar with the terminologies and the concepts, just a little bit, and hopefully by the end of this course, I'll be, able to speak about it, to other people.
Perfect. We're very excited to have you on board.
Thank you.
Hey, Matt, can you hear me?
I can, yes.
Hey, thanks. Matt, right now in your presentation, the entanglement and subsequently the teleportation was between like two different qubits, right? Theoretically, teleportation can be achieved for multiple qubits as well. Is there any way in your simulation we can achieve that, like just for the sake of experimentation?
Oh boy, that would be quite the homework assignment. Well, I'll tell you what. So this material is going to be the fodder for training quantum engineers in my company. And what you may have just given me is a really good homework assignment for all these quantum engineers that I'm going to induce pain and suffering on. And so maybe I'll take that and make sure that's a homework assignment for these guys as they come through, and then see what they come up with. But I have not done that. I've done it just simply for two. We need to start with the basics just to get the concepts across.
Sure.
I don't know how that would work out. I think that's an excellent project. Maybe I'll pass that along.
Yeah, having said that, I mean, this presentation, whatever you've shown is actually an eye-opener for me too, because I never visualized teleportation in this same way. The teleportation to me was a little bit different altogether, but the way you have explained is wonderful. So thank you very much for that. I'm just curious. That's why I asked that question, like what happens to multiple qubit and teleportation when it happens. So thank you again.
You're welcome.
Todd, I think you had your hand up. You see that? See that, Matt?
I did. I think I figured it out though. So I think I'm good. My question was about Quark and the message that's there. So in the teleportation, it's actually scroll down, yeah. Yeah, right there. So that message there, is that just a generic qubit, like alpha 0 plus beta 1?
This thing here actually what
Yeah.
that is you can manufacture your own gates. There's a make gate thing here, and this is generally a combination of the rotations, X, Y, and Z. It's sort of all three combined that sort of makes a random rotation around the black sphere surface.
Right. So it's not just some random gate. It's not a random combination of amplitudes.
No, it's sort of a fusion of the formulaic gates that they have here.
Okay.
And I stole that idea from the guy who invented Quark. He always had this gate, and it was always doing this kind of thing. I'm like, how did that happen? So I sort of pilfered that and made sure I reused it. It's such a great gate for illustrative purposes, because you can literally see like it's feeding a surface area point that's more or less continuous. It's sort of just revolving around here. And the beauty of this is we can actually watch it get recreated down here, and you can see that like each movement on the surface of this sphere is a teleported state. And as you can see, that constant movement of states across this conduit is continuous, and it's for the first person looking at this, it really kind of brings the concept home.
I have one question. How did you get this output on Python? Like, I'm very new to Python as well. I only know like you put the code and you get the output, but this is more like a visual something.
Yeah, so this is the Quark quantum circuit simulator. You can look it up online, and it's a web-based visual thing. So this is literally a, like if I go here and pull this off, give me a second here, I'll pull this up, go like that, go like this, we get Quark, and we can edit a circuit, and we've got the whole thing. So it's a pet project of a really smart engineer who wanted to put sophisticated tools. It's kind of a toy, but it's a sophisticated toy. For our purposes, it's wonderful for instruction. And you can literally, you can create a gate, put a Hadamard gate here, put a C0 gate there, and all of a sudden we have an entanglement gate going on there.
That's amazing.
There's a lot of digging through the internet to find some of these tools that I thought were worthy of explanatory purposes for the folks just coming into this. Now, if I was a quantum, if I was a quantum PhD, this would be boring, but for everyone else, it's kind of interesting.
How much time does it take for you to put it all together, find all these amazing resources?
So for these 7 modules that I've got start to finish, it's about 5 months worth of work.
Wow.
So other questions? Who do we have on? Who have we not heard from? We've got Galiston out there.
Hi. Can you hear me?
I can.
Hi. So I'm Harshita, and I have a question very specific to today's tutorial. So you entangled the EP, the entangled pair, and the Bob's qubit first.
The entangled pair up here.
That's it. So in the teleportation itself.
Oh, teleportation. There we go.
Yeah, that's it.
Okay.
So first of all, you first entangled the EP qubit and the Bob qubit first.
Correct.
Right. So what happens if I first entangled the Alice and the EP qubit?
Well, you have to understand why we did this. So we had to entangle. This is our communication, our quantum communication conduit. That's what this one is for. And initially what we do is we entangle Bob because he's kind of in a passive state right here. He's not going to do anything. He's on the receiving end of this. And we have to, at least at this point, have Alice not be part of this entanglement just yet. Because she's got to independently prepare a payload to stick on that communication channel. And that's why you see the entanglement occur with the conduit as well as Bob first. He's in a passive state. He's going to receive stuff. He's not going to be putting stuff on there. Alice is going to be the one who's active in that spot. So she'll create the payload, and then she'll engage in the entanglement herself, and then she'll have a couple of other activities here that maintain, that get executed to maintain the phase and the magnitude information. And then she'll read it, she'll execute a read that actually pushes that information onto that entangled qubit and then down.
Okay, I got it now. I got it. A follow-up, please.
Yes, ma'am.
So somebody talked about the multi-party teleportation, right?
Right.
So what do you think? So would we have to would we have to entangle all the qubits present in the multi-party teleportation, or is it just, or will it just be Bob and Alice who are connected?
Well,
so the sending and the receiving end should be connected, or all the qubits in the multi-party system should be connected?
So it depends on what you want to do. I've not gone that far. So, and I can just do a thought experiment in that, and that's as far as I can take you. So I would rather not approach that because I suspect that my thought experiment would be flawed right out of the gate. But I do think that's something that we'll look into. You know, the idea of multiple qubits in a scenario like this would probably be for fault tolerance, you know, that kind of thing. And I believe anybody who's taken the MIT X course, I kind of remember those guys articulating multiple qubits in a situation like this for fault tolerance, but I'm not sure. Now, other times, if you're doing, I don't know if Keeper's still on the line, if you're doing quantum chemistry and you're doing some unique modeling of molecular movements that the entanglement of multiple qubits could help out in that space. Keeper, can you shine any light on that from your perspective? Because that is your space. No, she's not coming off mute. All right, maybe we'll catch her later. So yeah, hopefully that helps. But
Here I am, sir.
Oh, there you are.
I'm on my cell phone, not on a computer, so it's kind of going on and off mute. It's kind of difficult sometimes. Okay, so can you rephrase your question so that I can understand better how to phrase my answer?
So I think the question I'm gonna, if I get this wrong, let me know. But the question was, okay, so we've got a scenario where we're doing just quantum teleportation. Now you're on a cell phone, so you can't see this, but you know, you've got entangled photons. You've got Alice and Bob. Alice kind of combines her photon and ships a couple bits to Bob and reconstitutes the phase over, or the state of the photon over by Bob. So standard stuff. And the question ended up, well, what happens when we use multiple? I mean, that's just a couple of qubits, but what happens if we use multiple entanglements of qubits moving forward? What does that do? And the thought for the quantum networking was that adds redundancy, but my thought for you is that could play I wonder if that plays a big role in the quantum chemistry, the molecular modeling side of the house. And that's why I wanted to kind of tap you on the shoulder and see what you thought.
Yes. So from my perspective, if you want to think about more than just Alice and Bob and you have multiple players, that's when I think having multiple qubits and entangling multiple states would be beneficial, because now you're communicating not just in, you know, one direction, but you have multiple directions, and that would be, you know, very analogous to, you know, quantum chemistry states, in the sense that we have multiple directions where we could have entangled particles and understanding that dynamic. So yes, I think extending it from Alice and Bob to, you know, hundreds or even millions of people in the network. Does that answer the question, do you think?
I think that's probably the best answer we've had all day. So, Shardy, was that good?
Yeah, that was very on point. Thank you, Keeper.
You're welcome.
Thank you, Matthew. Thank you.
You are very welcome. Other folks, we've got, was it Yefim Surf at the very bottom? And we've got Jamie on board. Laura O is on board as well. Anybody want to ask a question? We've got Mark Jack as well.
Hi, this is Mark. I appreciate the presentation. I mean, that was amazing, especially the visualizations. I used to do physics a while back, have a PhD in the field, but switched to industry a couple of years ago. I'm basically studying out of Jack Hidari's book. And I'm kind of right there where you basically are doing the presentation today, quantum teleportation, entanglement. So that was really useful. I was wondering whether you could kind of, well, the time has already progressed somewhat. I was kind of curious how the first couple of slides and the first two workshops you guys did, how they look like, but I can also look at the materials offline. But I really like the quantum teleportation explanation on the classical connection that's necessary, because I never really understood that. Especially that whole being able to transport information faster than the speed of light. Of course, I cannot possibly believe in that as a physicist, but I could not quite understand how that worked in quantum teleportation, so that helped. Thanks so much for that.
You're welcome. So I think if any of you who are going to Quantum Tech, that Quantum Tech week-long conference, they're going to advertise this series there, and then we'll set up time to actually execute the series later on in the year. So this material will be out in the public again.
Cool. Thanks so much.
Appreciate it.
But we've got the recordings from the first 2 sessions available right now.
Right. All right.
Thank you.
Oh, you're welcome, sir. We've got Deb Goschel and Dan Stubbs and a number of other folks. Don't be shy, folks.
Hi, this is
Yeah, Keeper here. I have a question. So you gave an example of entanglement in a human condition through marriage, and I'm considering, how do we understand the human element and being able to tie in, quantum computing, and what are the ethical approaches behind understanding these various human entangled states, you could say, and is there anything being done out in the, in the corporations to address, what are we using these states for in determining and predicting, human properties? Is that happening right now?
So I can tell you our perspective. So I don't know if everybody knows, but I work for Optum Technologies. We're the technology arm of UHG, United Healthcare, and we're the big 500-pound gorilla out there, Fortune 5 domestic U.S., Fortune 15 worldwide. And my background in that area is in the AI space, artificial intelligence. Quantum's just one of the passions I bring on board. I do the spectrum of AI from end to end, not just the data science, machine learning, deep learning side. But one of the things we realized in our space, like we're the evil insurance company, and in our space, we had to address the court of public appeals, the court of public opinion. What are you guys doing with AI? Are you going to build, we're never going to build killer robots. The military, on the other hand, I was an AI engineer for a military contractor before coming to Optum. They will build killer robots, so that's a whole different story. But one of the things we realize is that we have to address the ethics side of the fence, because that's an ongoing concern, and it's getting out there. And the way we do that is that I'm also responsible for, I wear many hats in Optum, but I'm part of what we call Optum Tech University, the College of Artificial Intelligence. It's Optum teaching Optum, but in this case, it's Optum teaching Optum in AI. We've got all kinds of courses, and one of those courses that's mandated, absolutely, you come through our program, you're going to have to take it, a number of ethics courses in artificial intelligence, particularly geared towards the data side. How do you, the data acquisition for the data orientation side of that. So machine learning, deep learning, that kind of stuff, prediction, classifications. There's a lot of ethics in regard to that that needs to be addressed. And I think the industry in general is getting better at that. You could do that. That's stuff that we are able to do. Where we can't do it, though, it's in reasoning. So AI is more than just data science, machine learning, deep learning. AI can cascade into cognitive technologies. We introduced that where we're coming from the cognitive science camp. And we're using artificial general intelligence. It's called SOAR, S-O-A-R, State Operating Result. It's a framework that we're using. The military is using it too, because it's been growing for the last 35 years. But we can solve reasoning over context problems in the clinical domain because it's not replacing the decision-making capability. It's augmenting it. So if you ever play Halo or Mass Effect and you see Cortana or Sam in Mass Effect Andromeda, those are augmentations to human intelligence. They're fantastic and extraordinarily powerful, but they never replace it. Like in the military, there's never an AI behind that gun going to shoot it, pull the trigger, anything like that. It's just not going to happen. But you can have those augmentations. And so in the clinical space, when we're making life and death decisions in the operating room or on the nursing floor or out in the wild doing population health, those augmentations to human intelligence to understand the breadth and depth of the case, and I've got decks I can share with you on this, matter. But the human's always going to make that decision at the end of the day, and we want to take the burden of crunching the numbers away from the human and have them. It's a phrase we use in the nursing space that, or the clinical space. We want those guys to practice at the top of their license. You know, they're practitioners. They've been trained in medicine. We don't want them to be data clerks. We want them to be medical professionals. And so let the AI do all the clerking for them, and they can practice at the top of their license. So that's the other side of the coin, but we make every engineer comes to the College of AI and Optum Tech University, they have to take an ethics class or two. And so that's how we're addressing that. Hopefully that, it's a bigger answer to the question, Keeper, but hopefully that's got, that covers the basis.
Yes, that was great. Thank you.
You're welcome. All right, anything else? There was another couple of hands that went up.
Sanjay?
Yes, I had another question. So looking at, when we were talking about teleportation and multiple qubits. So my question is around efficiency and reliability of teleportation. And I know that for a single qubit, it's whatever the efficiency is, it's a given. And I guess theoretically it's 100% reliable. But if we scale this up to, let's say, 100 qubits, or let's say 2 to the 100 qubits, right? Would the efficiency of that patient be affected? And also, would the reliability of that be affected in any way?
So I know for a fact that Alex Kahn, who's on this line, also took those MITx quantum courses at the same time I did. And I'm going to punt to him and see if he can come off of mute and if he can remember any of the quantum networking conversations that were going on there with the fidelity issue. Alex, do you remember any of those?
Issues with fidelity on quantum networks?
Right, with multiple qubits, redundancy, and all of that.
It's not an area I've been focusing on for the last year.
Okay. So
what was the question, though?
Well, the question, it was in that quantum networking space, teleportation space. The teleportation has to be used to do quantum networking because we can't copy qubits.
Yeah.
Can we?
Yeah, so they're making. I mean, I think the main key thing is the quantum repeater. So I think in our current lines, optical cables, for example, you cannot transmit information beyond a certain amount of distance because of decoherence, and you just lose the information even though it's transmitted. Let's say the photon is transmitted with many lasers or many beams of light. Eventually, it just there's so much decoherence that that information is lost. But if you put a repeater in between, and the repeater has to use some of that entanglement, because you cannot copy a qubit, but you have to do it in a special way so that you retain the information, and it has to be entangled from end to end. So then you're able to put the repeater in between before all of the streams of photons actually lose information, so you can get enough information to repeat it and keep moving forward. Then you can transmit that information, at least on an optical cable. And but I believe the whole system has to be entangled, because you can't measure it in between. You lose information that way. So the whole thing has to be entangled. And then the question becomes, can your repeaters be synchronized enough to transmit the information and hold that information for the time it gets to the other end without losing decoherence? So that's my general information on that topic.
I think you did a great job. That's why I punted to you. I figured you probably would remember that better than me.
So on the other hand, I mean, there's communication with the photons going to satellites, and that's a totally different topic. I was talking about optical cables, but I mean, there's other communications going on with satellites as well. China did that. I think the US is doing some experiments on that. So I don't know the details on how they're ensuring that they get all the information, but they are using entanglement as well.
Agreed. Terrell, back to you. Oh, you're on mute, sir.
Yeah, the spacebar thing only works if the cursor's in the right spot. I was going to say, I can't answer that question about networking. Anyway, well, Sanjay, I think, was it, I thought I saw another hand up, but if not, last call.
I think there is one hand up, Pakrith Musire. Nope, that's just a thumb up. So I think that's
Hey,
it.
sorry, no, it's a thumbs up. Yeah, when you had like 8 minutes break,
Okay.
there are many questions that I have anyway. So one of the things, like China claimed they did quantum teleportation, right, using their quantum satellite. But do you guys know if anybody has verified that data? I mean, I'm just asking out of curiosity.
Oh,
Great
boy.
question. Great question.
Yeah, that's oh, Terrell's now on mute again. So I don't know. I really don't know, but I do know that there's the conflict, the conflict between the U.S. and China in both the artificial intelligence space and in the quantum computing space is good for us. Now, nobody likes conflict, but what that did was, you know, if you look at the potential for geopolitical global dominance, that's literally what's at stake in this. It's almost like when we sent the first man to the moon, the technological runoff from that that process put us in the lead technologically globally. And I think a number of strategists that I've talked to and futurists and things like that who look at this this scenario all tend to agree that this open warfare, open conflict between the U.S. and China, and it's open. I mean, it's not a cold one. They've come out and said, we're going to win this race. They realize there's geopolitical dominance for decades at stake here. The U.S. has come back and said, hey, we're going to win it as well. And both areas are mobilizing vast resources, financial and academic and industry partners and things like that. And that can only serve for the folks here on the phone and elsewhere who are first movers to be a really good thing, because now it's pushing this into the limelight. There was another recent article at the governmental level that was a movement from some senators in the U.S. to make quantum computing a primary concern and a responsibility that every company has to sort of come to the forefront and make statements about, like, hey, we're going to get a quantum computing workforce ready and all that. All of these things are happening. And the larger geopolitical conflict aside, you know, if that can be mitigated, the propulsion effect of that for quantum computing is going to be what's shortening the timeline and getting companies more interested in what's going on, and that can only benefit us. So that's really an important space geopolitically to follow, and it's something that futurists are looking at, that consultants are looking at, that you know, government strategists are looking at. It's a big, very important place, and we should have our fingers on that as well.
Getting to the very first part of that question, I would add that, no, I don't believe the Chinese did it. Period.
Yeah, because there are few things that really that really comes in my mind is, like, a satellite is not a static object. It moves at like 800 or something kilometers per minute speed. And then you're sending, prior to the satellite launch, you need to entangle 2 qubits, and you need to put one of the entangled qubit in one of the satellites, and then you put it up on the sky, and then the rest other qubit stays on the earth, right, in some space or some communication station or something, and then you try to send a message from which should bring the essence of quantum teleportation or quantum entanglement. That's a very tricky thing, and we need to verify that claim that they really teleported the message between 2 entangled qubits between Earth and satellite. I mean, the claim
You could just ignore it instead of verify it.
Yeah. All right, thanks. I mean, I didn't want to ask this question, but it just came out in my mind because you were mentioning about that. Yeah.
I do think there are
Thank
papers
you.
out there. There are papers out there of what the Chinese actually did for that experiment. And I don't think it's about storing qubits in space. It's more about entangling photons and bouncing them off to different places. So if you did a search for, Chinese satellite quantum, you could probably find the paper, and I don't really remember the name of it, but there are details in it which you can at least look at.
Okay.
Yeah, just to add to that, in general, people aren't trying to keep secrets. They're trying to let people know what they're doing because they want other people to build on it and make it better.
Well, I'm burned out today. Okay.
Oh, Terrell, you're on mute again. Yep, you're still on mute.
There we go. Okay. The cursor has to be on the Zoom window for the spacebar trick to work. If you hit your mouse and move it off, you're screwed. Anyway, yeah, any other comments, questions? Matthew, you're right. This is a short one tonight.
Yeah, it's a short one on when we get into quantum algorithms and quantum problems and practicals. This one's particularly dense. There's an awful lot of material here that we're going to really dig into that I think will kind of move the needle a little bit. And then when we get into some problems and practicals on Friday, there's a whole lot of really cool things in here. We'll take another case study and look at a few other things in detail. But those are more dense, and hopefully that will add, and we'll kick off with a little bit of quantum machine learning at the end of that. But I think that'll start to add some more real meat to the series, and hopefully you'll find that interesting as well. Oh, Terrell, you're on mute again.
Okay. I said I'm sure we will find it interesting. All right. Well, that's it for tonight, folks. Let me just remind you, if I can quickly steal the screen for a second.
There we go.
Got it. Boom, boom, boom. We got a slew of stuff this week coming out of the Philadelphia Harrisburg program. So Matt was today, thank you. And let me see. Tomorrow night, I'm doing complex numbers. If any of you beginners are out there, it'll be a follow-up on the first round of complex numbers. So I'm just going through the real basic stuff. We'll have a little bit of trigonometry in there, which is necessary. And then Wednesday night, Matt's back there. And then I'm going to give a talk on quantum cryptography and quantum key distribution. Nothing nearly like what Matt presented there. I'm much more hand wavy, but that might be interesting for the newcomers to this space. And then Matt again on Friday. So we've got something going on each day this week, and plenty of other material coming up. And by the way, I haven't mentioned this, but Microsoft has a Q-Sharp coding contest coming up for you home gamers, and it's in the Quantumapalooza site if you want to get the details. But there's a whole slew of other things going on this week, including IBM's webinars. Here's a Rigetti talk. Sandra Kaiser has her event on, what's the name of that, Twitch. So if you, here we got one coming up on Wednesday afternoon. Oh, this is by Q World, guys out in in Eastern Europe. And also tomorrow, any newcomers, by the way, this is by Qmunity, tomorrow at 4 o'clock. This is a group of high school kids that are passionate about quantum learning and teaching, etc. And it's all ages type of thing. So last week or two, they had an event, and there were a bunch of us 60-year-olders attending it, and it was not a problem. So that would be a good program to check out if you got time tomorrow at 4 o'clock. Anyway, I'll just cut it out from there. Good night.
All right. Thanks, everyone, for taking time to come to this speech, and we look forward to seeing all of you on Wednesday.
Yep.
Well, thank you.
Bye-bye.
Thank you. Bye-bye.
Sayonara.